Okay, so good morning. Welcome to this session. I feel the pressure of collectively waking all of us up. So yeah, I mean, in case you haven't woken up, I hope that I'll not be boring, that I will further put you back to sleep. But anyway, so this talk, this chronicles the journey that myself and the security researchers of our team we took while we were trying to understand and evaluate the security practices that are happening in Zephyr and how much that is working and if there's any need for improvement or not. So before we go into this, just give a little bit of background of myself. I have been doing static analysis, bug detection, and bug fixing for almost all of my life, about 20 years now. I like to think that I don't look that old, but apparently I am. I've been around and seen a lot of these bug detection tools evolve and mature and where they are right now. Specifically, the work started from my PhD years at University of Illinois at Urbana-Champaign. And my PhD thesis, it focused on asking that question, and it was the first work that asked that question, why stop at detecting bugs? Why can't we also automatically fix bugs in the first place? That was back in 2008, 2009, so quite a long time ago, before any of these LLMs or any bug fixing capability. Actually, bug fixing capability is still not there. But that's where it asked the question. Then I went into academia. I did a lot of research on how do we build tools for automatically fixing bugs. Specifically, I focused on C code. So in 2012, my students and we wrote a paper that was looking into a general purpose problem in C code and seeing whether we can build a tool to fix that problem. And we were focusing on 4 kinds of integer-related issues: integer overflow, integer underflow, integer sign mismatch, and integer width mismatch. So 4 of these kind of issues, and can we build a tool to detect and also fix those issues? And that was kind of the grandfather of OpenRefactory, which is my company now. But that particular tool or that particular research work was identified as the best computer science research in all disciplines of computer science in 2012. And this was my student and I, we were awarded at the Turing Award ceremony in 2013. So that was like the start of building tools. And then I moved into industry. I worked at Coverity, which is the leading bug detection company in C++ space specifically. But in general, it's a very prominent company, now part of Synopsys. I worked there for a couple of years. I had first-hand experience of the way the C++ tool is built. But at the same time, I was more focusing on, or my team was more focusing on, we were bringing the JavaScript capability into market and also Android bug detection tools. So those were my primary responsibilities. But I know underlyingly like how the stack works and and how the detection algorithms, et cetera, work in order to detect the bugs that Coverity does very well compared to the rest of the market. And then I started OpenRefactory. We received an award from the National Science Foundation to take our work that we were doing back in the academia into industries, and we started building a C tool because that was what our expertise was. We built a tool, but then we ran into some product market fit issues. That's a separate story that I can tell offline at some point. But long story short, right now, so our product is called Intelligent Code Repair. Right now, we are focusing on Java, Python, and Go. And this year, we are again building a C 2.0. We already have a C 1.0 that we don't sell from our company at this point, but we are building a C 2.0, and that's how kind of all of this work or the planning of the talk started. And we're also working on Rust right now. So at the end, near the end of the year, we're going to bring tool. So just one more plug about OpenRefactory. What we are doing is we are identifying the fundamental problems in the bug detection tool space and trying to fix them. And specifically, there are 3 problems. There's the bug detection tools. They don't find the really hard ones. They find a lot of stuff, but they don't find the really hard ones for you. The classic story is Coverity was used in the OpenSSL stack or CI/CD pipeline between 2012 and 2014 when the Heartbleed bug was introduced. Or no, it's a bug that was introduced, and then eventually when it was detected and catastrophically blown up out of proportions. But it was there all along. It was scanning and never finding anything. Then there is the false positive issue, that the tools generate a ton of false positives. And I'll show some of those examples in this talk later. At the same time, as we discussed, that the current static analysis tools, they all stop at detecting bugs. But I mean, we are here, AI is beckoning on us. Even without that, our computers are computationally much more powerful than we were in like 2008 when we started asking I started asking the question. So it's almost unconscionable, like why don't we have tools that can also automatically fix these bugs for us in some of the cases. So that's what our product, Intelligent Code Repair, is trying to solve. We are finding more critical bugs. We are also doing that with dramatically low false positive. We have less than 5% false positives on benchmark tests compared to whereas the other industry tools, they give you between 70 to 90% false positives. So 10 bugs that they identify, 9 of them are probably wrong. It gets better for some tools, of course, but that's like the other end of the side. And then we are the first tool in this space that also is able to automatically synthesize fixes. So for all the bugs that we detect, about 50% of the cases, we are also able to automatically synthesize fixes. And right now, this capability, again, is available for Java, Python, and Go. We are building the C tool, and when it is there, we hope that these OpenRefactory promises will be reflected in there as well. But before we go into that, just about the finding more critical bugs. So in 2014, when Heartbleed came out, at that point, my students and I, we already moved on, and we wrote another paper, this time also building another tool that is focusing on these buffer overread and underread vulnerabilities. This was already published at that point. We had a prototype tool that's going, and we were wondering, okay, there's this big vulnerability that came out in OpenSSL. Can we detect that? And we were not only able to detect that, we were also able to fix that. That's where our capability was at that point. And when we go back again and build the tool, again, we want to bring that particular aspect. So we were there in the academia, and I didn't know like how to marketize this thing and such, because we were just interested in writing papers and solving theoretical problems of the world. But here I am right now trying to take everything or all of these lessons that we have learned from the academic research, theoretical research, very passionate stuff, but then how much of that can transport into market and be useful for all of us. So also a little bit of background of what we do in OpenRefactory. We are right now working on scaling thorough security audit and scaling that to a large amount of projects. And the problem here is the tons of false positives that the existing static analysis tools generate. So if we are scanning, let's say, 100 projects, and each one of them is getting 100 extra false positives, that's about 10,000 false positives. And if you take 10 minutes of time to triage a bug to identify whether it's a false positive or not, that's about 100,000 minutes, a lot of time. And so clearly that doesn't scale well. So how can we scale security audits and do a lot of that? So right now we're working with Alpha Omega and Linux Foundation and Python Software Foundation. We had a bigger scope before, but now we have narrowed down the scope of work. We are focusing on the top 2,000 Python open source projects in the PyPI library based on the number of downloads in the last 1 year. And our mission is very simple. We want to scan those projects, identify if there's any bugs in them, report it to the maintainers, and then occasionally provide fixes because we can, and then also work with the maintainers to get the problem fixed. So go the entire mile of delivery for that. And so specifically because there's bugs everywhere, but then some bugs are more critical than the others. So we are focusing on just 32 different kinds of critical security problems. These are identified by the CWEs, also the OWASP list, and so on, as in what are the critical bugs in that space. We're just concentrating on that, not bothering with the minor like bugs here and there. We sometimes report those, but that's not the focus. This particular work is looking at that. And so in the last 5 months, we had about 350 bugs that we detected, 120 of them security related, 40 of them high severity. About 60% of the bugs that we reported already got fixed, accepted by the maintainers and got fixed. So what this has shown that we can take the work and do that at scale, and do a whole lot of good. And so several CVEs, et cetera, have been assigned and are in process of being assigned, and so on. So that's the work that we were doing. So I gave a talk at the OSS summit in Japan in December about this work. This was just the start, so we were only about a couple of months within that. I was sharing the results. So Kate Stewart, who is one of the champions of Zephyr project, she was there. She just finished her keynote. It was also another early morning talk. I don't know whether they feel like I'm very energized and get all of you guys wake up. So they scheduled me for early morning talks. So Kate Stewart, she just gave a keynote and just came after that to my talk. And so she was very interested about what we are doing, whether we have any plans working with C. And yes, we were thinking of doing or going into that space. And so the plan was, okay, how about we project at this point and basically, it works for us as well, because from our side, we are looking for feedback from the community or understanding from the community. I've been working on C, as I mentioned, for long time ago. So I have a general understanding of what bugs are more important for the C developers, but things may have evolved. I haven't looked into C very closely in the last 6 to 8 years, and things could evolve. So it would be good to get feedback from our side, from the Zephyr community, and one way of getting feedback is to just look into the audit process, look into the process of what are the tools that are being used by the Zephyr community for detecting these security bugs, and are they working? What kind of bugs are getting reported? What kind of bugs are getting fixed? Is it any different from what we have seen before or has evolved, and so on? So that was naturally also very interesting from us, and we were not. So we, based on our plan, our C product is going to be coming later in the year. So we wish that by the time this talk happened, we would have some operational version of our C tool and see how that works. But that was not part of the plan. It was more about just giving a thorough look, because we also do the security audits in the other spaces and so on. Give a thorough look about what is happening in this part of the world and how are things working. So that was kind of how this talk was planned back in December. Then obviously went to the CFP process, etc. What is interesting was in October in Zephyr version 3.5, code checker was also introduced, and that was it was one of the main things. And then there's this push towards more security scans or more actionable items coming out of the security scans, and whether they're useful or not. So that kind of questioning, retrospection is happening in the community. So we thought it's a good synergy. So let's have a look at that. So that's basically how the talk started, what my background was, and then how we went through this. So here's a plan of this particular talk. We use the term root canal. This is a term that is borrowed from code rewriting or refactoring literature, where I come from. Where we are rewriting code to fix problems. So in refactoring literature, there are two terms that are being used. There's a floss refactoring and a root canal refactoring. And the floss refactoring is basically you do some small changes in the code. Most often there are tools that are available there, and you just find small bugs, small ubiquitous problems. That's what the standard term is for that, and you fix those problems. So that's typically takes a couple of hours, a few minutes, couple of hours, at most a day of your time, and that's where it is. And then there is root canal refactorings, where it takes a lot of effort. It goes beyond tools because there are, like, for such a big scale of refactorings, often all the steps are not supported by any refactoring tool. So you look at those and you try to, like, some parts of that is manual, and through a combination of automated tools and manual process over a period of few days, you make some major changes in that. So we had to give a catchy term name to the talk that came in. What we wanted to do was also look at the tools and also do the manual triaging of that, manual understanding, manual exploration, that way, over a course of time for a long period, and look into, like, what is the static analysis tools, how they're being used, and so on. So as part of this talk, building up this, we interviewed the maintainers about the best practices. We evaluated the results from some of the current practices. And we also analyzed the source code using some other solutions that are out there, whether there's some gap that is there and needs to be fixed by something else. So that's what the experience that I'll be sharing in this talk. So right now, Coverity Scanner is the one that is used in the CI/CD pipeline. It has been there for some time. What we did was we narrowed the scope and we looked into all the bugs that were reported by Coverity between January 2024 and March 31, 2024, 3 months of time. And these reports were all public, so you can go to GitHub and you can search with Coverity issue tag and you will be able to look at them. So it does, because the bugs are generated or reported automatically, it has the robot generated issue tag there, so it's very easy to find them. And but the bug reports, they typically do not have that much explanation. Oftentimes it says that it's just a heading that, okay, this is a bug, and then for more look into this, and then they are pointing to Coverity portal, which I did not have access to. So in some of the cases, when we looked into these bugs, we hoped that we would be able to look into more closely about and give our judgment of whether this is a true positive or false positive or not. But in many of the cases, we were not able to do that. We were only looking at the GitHub commits and so on and getting that. But in this particular aspect, or for these particular things, we more relied on how the community responded to the bugs. And the community response was actually pretty good. So there were total 77 bugs reported in those 90 days of time. There were 11 bugs that were duplicates. So we are talking about 66 bugs over a course of 3 months. That's actually pretty good for a bug detection tool. And of them, 35 unique bugs are already fixed. So that's a very good fix rate. About 50% of the bugs that have been reported have already been fixed. There's been about 25% of the cases where there are false positives. And these are identified, again, not by us, by the maintainers themselves. And so that's what we did, or what we looked into. There's 17 bugs that are still pending. These are the bugs where we were interested to see whether we can find more about that and see, like, okay, are they pending because of some false positive or not? But again, because of the lack of information, we couldn't go much into that. But that's where we are. There's about 25% of the bugs that are being suspended, and they can go either way, this way or that way. But typically what happens is the higher priority bugs, they get prioritized, and therefore they get fixed faster. And the ones that are low priority, they typically, the ones that take longer time, there is a chance that they will probably be erring on the false positive side as well. And so most of the bugs that were identified were of medium severity, about 2/3 of them, but then there's about 20% of the cases where some high severity bugs were found. Many of the, majority of them have already been fixed. There's a few that have been labeled as high severity by Coverity, but then the community is not necessarily sure about that, but that's what the lay of the land is. So here's a sample of a high severity bug that was reported in Coverity. So in this case, there is this comparison that Coverity flagged, and there is a macro that is being used, config num IRQs. There's a comparison done between table IDX being greater than config num IRQs before we are writing into the table IDX. So it's important that we do not write beyond the buffer bounds. And there is an check that is already established there. The question is whether this is a useful check or not. And so this is a bug that was flagged. So we went into like what is the definition of this, and it is multiple defined under multiple different configurations, but it basically look into the different IRQs and different signal levels of interrupts, and then creating a sum of stuff based on that. However, there's this config num IRQs. There's also there's another corresponding check which is about the IRQ table size. So when we are writing into the table, it's better to look into the not the number of things that can be on the table, but also the table size, because in this case, because there's a start vector, there's a padding up front, so therefore the number of the table size is actually smaller. So if we were looking at just the aggregate, the sum based on the config num IRQs, it will take you, or it might take you beyond the buffer bounds. This is pretty clever. Actually, what Coverity did was it figured out the macro definitions. It did some length analysis, identified like, well, what is the length of the buffer and what could the access be, and so on, and reported the bug. And so the fix there was to move from the config num IRQs to the more reliable or actually the real metric that we should test against. So if it is greater than equal to the IRQ table size, it should be able to flag. So that was the fix that got added, and so on. So that's and not surprisingly related with buffers, whether you are writing, reading within or outside the buffer bounds. I mean, that's been where C people have been there forever. So so that's one of the bugs that were identified and also fixed. Now there are some also, here's an example of a medium severity bug. This is pretty straightforward actually. Not very, it doesn't need a very clever tool to figure this out. But there's this function call in the red side, red line in line 2515. There's a function call that is there, and it is supposed to return some value and some error code as well, but there's no check on the error code. So it's just like creating a receiver and then assigning the error code and doing a check of the error code in that. Now in the second case, the fix, so I'm looking at it from a tool builder's hat, like can we build a tool? In the first case, the tool is, there's a tool that can easily be built. In that case, you just create a receiver, you just add a check, basically create a bypass, and that's that. What you're not doing there, however, is what happens if error is 0 in this case, or there's some error that has happened. What do you do there? Do you bail out? Do you crash and burn? Do you just print something and just move on? that's something that a tool builder cannot identify. So, and no way, it requires information that is domain specific, and specifically the maintainers need to come with that. So what it did in this case is, in the first one, it just did a bypass, but it did not say what is happening in the other side of the bypass. But it's probably okay, because in the bigger context of things, it's probably only doing something if error is if things are fine. But in this other case, there is some printout that's been added that probably logs and so on. So that's a sample of this. So now let's look at it in a different perspective. We also looked into what are the CVEs that were issued in Zephyr in all of its lifetime. So we looked into so there's a link underneath. This is also again publicly available. What are the CVEs that have been issued in this project for over a course of time? We see that in 2020, and perhaps because of COVID, we had more time, and so more bugs were, or more CVEs were assigned. 2023, I don't know, inflation maybe, whatever, yes. But so what is important is in 2024 so far, in the first 3 months, only 2 CVEs have been assigned and so on. So because we're talking about buffer overflow, and buffer overflows are important, we looked into the most recent buffer overflow that was identified here. This is in a case where sprintf was used, as you see in the code underneath, and it was writing beyond the buffer bound. It's actually given a severity level of 7.3, which is pretty high. So we looked into that. This is the fix that was added to fix that particular problem, where we added some length check and then replace the sprintf with memcopy and so on, and everything happened fine. So the fundamental thing about this is, and we have known this for a long time. Actually, the papers that we have written in 2010, 2011, 2012, back in the academia, we were all talking about this thing. There are functions that are fundamentally problematic, but we keep on using them. We keep on using star copy and star cat, even though we know that they're not good, and sprintf, even though we know that they're not good. And what's the challenge of just replacing them? And again, like, that goes back to my fundamental quest of why don't we have tools to, and in this case, the tool is not really hard to build even in many of the cases, because what we're doing is something in the static analysis parlance called length analysis, where the safe alternative of the functions that are there, they require an extra parameter, which is the length of the buffer. So the challenge for a tool is to identify the length of the buffer statically at a point of the program and use that information in the first place. So why can't we do that? So what we did was we just now did a GitHub search, identified like, okay, how many cases sprintf is used right now in Zephyr code? And so we identified that there are 68 cases right now. So we manually looked into all 68 of them. And so this is where I cannot do it just by myself. Our security research team, et cetera, helped us. We did divide and conquer on that. Most of the, I would say 67 of the 68 appear to be benign. They're okay to be used. One of them was a little bit interesting. So here's that one. So there's an sprintf which is printing out in this out.str buffer. It is printing a formatted string, and then there's some double values that are being used there. So, and that looked a little bit suspicious. And so this out.str, it has a size 64. So what we did here is we wanted to simulate a program, create a program that has similar standing. So this is basically the same or the similar program which has this same data structure that is being used, same functions that are being used there, but it is done in a small scope. Here, what we're doing is for values, we are providing maxint, as opposed to it can take any integer, but we're providing the maximum value that's available. Then this is printed to sprintf and so on. And now we are printing that particular thing. So we run this program. This looks to be benign, but actually there's a silent buffer overwrite that has happened here. So in this case, if we now create another buffer, so this format, because we're using maxin, the division, etc., it actually goes beyond the size of the buffer that's there. So we are just creating another buffer there, and we are adding another printf to see what that buffer is. Now we run that. Let's run that program, and now we see that even though we never did anything to overflow, it has the tail end of that previous one. Classic buffer overflow as there. Now you can tell, Munawar, why are you doing this? I mean, is this a 0 day? It's not. But this is coming in the samples code, so arguably, okay, it does not require that much scrutiny. Although in the recent wake of the XZ vulnerability, not everything is actually benign. Like, you might have to look into that. But what we did was we also looked into like whether this like out EV, like these values, how much of that can we control? And we were not 100% sure of whether that can be controlled or not. So we have brought this into attention, but that's something that I just wanted to show you. But fundamentally what this is coming back is to the question is, if we had we eliminated all the star copies and the sprintfs in this with a safe alternative of the function, all of these problems would be gone, because they are secure by design options for doing that. So, okay, so that's enough of Coverity. Now let's look into beyond Coverity. There's a code checker. I mentioned that was introduced in release 3.5. We spoke with the maintainers. We understood that this is only used, not in the CI/CD pipeline, but not only used by the end users. And so it's basically a openly available tool that the maintainers are making available to the end users so that they can run the scans themselves. And so it does not find much. So 0 bugs were found saying that code checker was used in this. But last year, actually even before code checker was used, there was a couple of bugs that were reported. One about an uninitialized variable. It's actually not, sorry, not uninitialized variable. It's actually unnecessarily initialized variable. So there was a variable that was initialized, but it's not needed there. So it's not a big deal, but it's that kind of bugs that's identified by code checker. This one was a copy paste bug though, and interestingly, Coverity did not find it, but they did, where they were looking into just copy paste. So this, like when this was done, this first line was just copied into the second line, and so there should be like new checks in there. And so it's a classic copy paste bug, but basically this tool was able to find it and in August of 2023 and not others. So what we also did was, now we looked into the new age tools like the sneaks and the semgrafs that we hear about, and then see like how much they work. So this is where we ran on sneak and semgraf. So sneak specifically identified a lot of stuff in the Python code and so on. That's another story. We can get into that. Specifically, we're interested in the C++ side. It identified about 40-something vulnerabilities. And then we manually triage. This is what we are good at. We, at our security team, we look at the bugs, we triage, we do the audit for and scale and so on. I've mentioned that. So out of the 41 bugs, there were 31 medium severities, 10 low severities bugs. So there was no high severity bug that were found. 27 of them were false positive. 14 of them, we are not sure whether they are true positives, but maybe worth a look, another look for the customers. Although we feel more strongly that those would also be false positives or not. So that's where the other tools that are finding in this space. And also we looked into semgraf. They have recently introduced a bug detection tool. They have identified 233 bugs in the C space. 3 of them were high severity, 60 medium, and 170 low severities. But there were only 2 potential true positive, and we also identified them as probably won't fix. But then 231 of them were false positive, so not worth anybody's time. So here's an example of a high severity bug that was identified as false positive. And this is what gives you an idea of like where the tools fail as well. So this was identified by semgrep under the rule local variable malloc free. So this expression points to a memory that has been freed. This can lead to a segmentation fault or memory consumption, memory corruption. So in line 403, it's flagging that, but this is just a free alternative, a library that is used to free stuff. And this is in the retarget lock close function. Where is it used? We look into the use of that. It is used in a test code, so okay, not that critical perhaps, but nevertheless, this is a library API, so it may be used in other cases. But here's a test code. But we see that there is a lock init that is happening. And so in the lock init, we do that. We look at that there's actual mallocs and there's these k-object allocs that are happening in line 365 and 367. So appears to be, everything appears to be in good order. So we allocated some stuff, we used that, and we did that. But why is it identifying that as local? And we were wondering, like, okay, I mean, this looks pretty unnecessary. Like, why would a tool find this kind of stuff? And so after a lot of soul searching, we thought that it might be that because this lock T, it is used as a parameter, but because this is a non-pointer parameter, or it appears to be a non-pointer parameter, then it might think that, okay, this is a local thing, and then not, and then that might be throwing it off. But we really don't know why it is identifying this as a local symbol as opposed to something that has been passed as a parameter. And actually, it's not a non-pointer either. So if we look into the lock T, the define in that same space, we identified that it's a void star. So it's actually passing a parameter by reference. So there's no problem here. Then we understood that, and then we looked into what sort of, so tree-sitter is the grammar that is used by GitHub that is also used in semgrep's tool. And so tree-sitter does not have any understanding of the macros. So to a tool builder which is building on top of tree-sitter, they're looking at this macro, and this is just identified as an int or something that is not a pointer. And then it is probably looking at a release of a pointer and just like, oh, okay, what's happening there? But it's really on the foundations on which you are being built that is creating this problem. So anyway, so this is a journey. This basically talked about what we have found and what is in this space. Overall, we feel that Zephyr has a very good security posture. It is using Coverity, which is the best in class in the tool right now. And as far as that is concerned, it is identifying quite a lot of bugs. There's arguably about half of the bugs are false positive, but it's okay as long as the other 50% that were identified as true positive, including high severity, have been fixed already. But it does not find anything, as we have seen that there are occasional cases where a code checker was able to find something that was not found by the typical static analysis, by the static analysis in the CI/CD pipeline. Other tools we have seen are occasionally useful, but in general, we have seen that they generate a lot of noise, so not being that useful. And so it comes back like that. There should be an active focus on coming up on tools that that can bring fixes or eliminate those classes of problems that we see recurringly from 1989. The first one, the first malware by Robert Tapp and Morris, the Morris worm. That was a buffer overflow. In 2024, we are still talking about buffer overflows. And from there to here, it's almost always like 80% of the cases are about uses of these unsafe functions. About 20% of the cases it's using, like doing pointer arithmetic wrongly. So why can't we build tools there? So that's kind of where we expect that OpenRefactory is going to be able to come and fill a gap, but at the same time, all the other tool builders should come in and do that. So thanks a lot for coming to this talk. I'd appreciate, if you have some questions, I'd be happy to answer. Yes?
I guess my big question is, we know functions like Esperit are unsafe. Has there been any effort just to disallow them and use code entirely?
I don't know that. I'm not a maintainer, I'm just a third-party auditor at this point. My interest, I've explained that earlier. So I don't know that as a fact, but here's a survey that I did in 2008 when I was a PhD student at that point and looking into these functions and wondering why are people using them. We looked into GoScript at that time, in 2008, and there were about 700 something star copies and star cats. So at that point, I was also doing empirical studies. So I did a small empirical study with the maintainers of that, identifying like, why can't we do that? And it really comes back to time and legacy stuff that's being there, and we just don't have time to do that. And had a tool been there or now or any time, and if it comes to a check of like, okay, somebody's next 1 month where they don't have to do all the hard work, but a tool is going to find those fixes. Somebody has to validate, run the test cases, and so on. That would have been great. We are just not there yet. But I don't know as a fact whether they're disallowing new users of sprintf, etc. in the code. And frankly, like we've identified that there were 68 cases of sprintf that are right now there. One of them looked a little bit suspicious. That's what I was playing on. But then 67 of them looked benign. So if a tool was just moving them from one to there just so that we don't have that problem in the first place, that's just good enough. Yes. Yes.
How do you deal with the fact that we don't write in C these days? We write in either Clang or GCC, which are not quite C languages. They have a bunch of extensions. They have a bunch of semantics. For instance, you can tag functions as malloc and free equivalents, function attributes. How do your tools deal with these more advanced languages beyond C?
It does if you provided metadata. Typically, like from my Coverity experience, what they did was they have a like a JSON data set where they kept track of, okay, these are mallocs, but these are what malloc likes. And then that can be something that is like you can configure it yourself, so you can add to that configuration, and then something that is malloc-like as identified by, let's say, Zephyr project, the tool can probably detect that. I mean, so.
Could you use the GCC and Clang attributes to automatically do that and accept that the language that you're evaluating is not C, but GCC or Clang?
That's a very good question. So if we were using, so depending on what parser you are building upon, in our case, for the tool that we are building, we actually have the parser entirely built for ourselves. So we understand whether this is a GCC extension or not. But in the case of Coverity, the parsing is done differently. I cannot say which one. But basically it is done by some other tool, and in that case, whether those information is available, I think that they should be available, but I mean, don't quote me on that. But I think in general, it's actually not that hard. Like there's the ANSYS that's there, and if you are writing or building up on a parser that is doing something else, then you can find that information. Yes.
How does the intelligent code repair play with like specific standards in an industry, let's say automotive or NIST compatible?
So Coverity is very good with that. Coverity actually, when I was there, they purchased a company from Australia called Goanna, which actually did MISRA compliance, and all of that was integrated into Coverity. We also aspire to be there, but yeah. So right now, for example, Coverity is very good with that. So it does identify those. Yes.
Yeah. You mentioned that your tool has very low false positives. What's the key idea behind it? Because we know that the static analysis has some non-deterministic issues, right? Because of the branch,
Yes.
concurrency or whatever. So what's the
And this is exactly where we come in. So we do path analysis better than anybody else. That's what we did in 2016 when we built the C tool and these benchmarks were tested. So there's the Summit benchmark, which is created by NIST and DHS, which has tens of thousands of C code, C and C++ code that has, and examples of programs that have subtle variations where something is vulnerable versus something is not. And all of those, in all of those cases, so that's where we ran our tool in 2016. And when we built our Java, Python, and Go tools, we also tested against the industry benchmarks, and we have seen similar results. What we did is, or what we do, which is different from what Coverity did and does now, and all the rest of the industry. Now everything is going into AI and LLM, which is even more scary because coming soon, more false positive for you. That's what I can project, if it is done only by LLM. But what we do is we do path analysis, so we actually follow the path. You cannot, however, follow the entire path of the program. That's just computationally intractable. However, we do SAT solving. We identify like whether this path is taken, and corresponding to that, another path is being taken. And what the secret sauce of us is, we scale that to millions of lines of code. That's what we have identified. And that's why our results are much better than the others. But again, not there yet with C. Hopefully sometime later in this year. It takes longer. So we will definitely not be the fastest, but it's not going to be so slow as in not what, I mean, you don't watch paints dry. So you run it as a nightly build. If in the morning you get bugs, that's good for you. What happened in the last 10 hours, you don't care. But let's say another tool is going to run it in like 10 minutes, will probably take 2 hours. In the end, if they give you 20 false positive, we give you 2, that's what matters. So yeah, that's what the hypothesis is. But we are the slowest, by far, yeah. Okay, thank you. Thanks a lot for your time. I hope I kept you awake. Thank you.